mark your calendars every second Wednesday of the month at 7 p.m. Some brief notes to share with you before we get started. We have carved out some time for questions as I know that's been a favorite part of these lectures. You can use the Q&A function at the bottom right-hand side of your screen. This lecture is being recorded and will be shared after the event. My name is Dawn Hart and I work for Wilfrid Laurier University. I am so proud of this partnership with the Milton Public Library. The Laurier Milton Lecture Series provides a wonderful opportunity to engage in a public dialogue with the citizens of Milton and beyond on a broad array of important topics. Presentations represent the current research and analysis from different faculties, departments, and programs at Laurier. I would like to personally thank the staff at the Milton Public Library for all of their hard work and support with this series. Before we begin tonight's program, we would like to acknowledge that Wilfrid Laurier University and its campuses are located on the Haldimand Tract, traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. This land is part of the Dish with One Spoon Treaty between the Haudenosaunee and Anishinaabe peoples and symbolizes the agreement to share and protect our resources and not to engage in conflict. The treaty was signed by the British with their allies, the Six Nations, after the American Revolution. Despite being the largest reserve demographically in Canada, those nations now reside on less than 5% of the original territory after losing much of the territory to settlement of newcomers. Perhaps you are joining us from another location this evening. If that is the case, I would encourage you to take a moment to acknowledge the Indigenous peoples of the lands where you reside. We recognize, honor, and respect these nations as the traditional stewards of the lands and water. I am now excited to introduce our speaker, Brandon Walker. Brandon is a research associate in the Arctic Hydrology Research Group located in the Cold Regions Research Center at Wilfrid Laurier University in Waterloo, Ontario. His research addresses how Arctic hydrological systems are changing under a rapidly warming climate. His research combines traditional cold regions hydrological techniques with remote sensing to better understand snow and stream hydrological regimes. Beyond research, Brandon is also the operations manager for the Trail Valley Creek Research Station located in the Western Arctic. When not in the field, he enjoys the outdoors and is an avid supporter of science communication. Follow closely with his ongoing research in the Canadian Western Arctic by following him on Twitter at Brandon0Walker. Tonight, Brandon will share some of the long-term trends in snow, water, and ice to understand how these Arctic systems are changing and how they may interact with other parts of the physical and human environments. Brandon, thank you for your time, energy, and knowledge this evening. I will now turn things over to you.
Thank you, Dawn, for that wonderful introduction. I'm just going to share my screen real quick here. And you should see my presentation there. Now, I wanted to talk a little bit today about some of our ongoing research that we have in our Western Arctic research site. So I wanted to talk a bit about some of the impacts of a rapidly warming climate on the Arctic water systems that we observe. Sorry, my PowerPoint is being overlaid here. There we go. So before I begin, I first wanted to take just a quick second to thank the many groups and research collaborators and funding partners who've made this work and this program possible. I also wanted to acknowledge that the research that I'm going to talk about today and our ongoing research takes place in the traditional territories of the Inuvialuit peoples, and that this research is conducted on the lands of the Inuvialuit settlement region located in Northwest Territories. So I wanted to take a moment to acknowledge that and also to thank our many local partners and community collaborators for their continued ongoing support with our research program in the north here. So I consider myself to be a cold regions hydrologist, which means that I just study water in northern regions. And a large interest of mine is studying the Arctic cryosphere, which is just studying the frozen landscape, frozen water. And what interests me in the Arctic, beyond the stunning landscapes and the amazing people that we've met, is the influence that it can have on the rest of the planet. You know, the Arctic and the land mass in the Arctic Circle takes up a very small portion of our planet, just under 5% of the land surface area, but it contains vast oceans and ice sheets and glaciers and contains and stores a large portion of our fresh water that we all rely on to live and function on this planet. And beyond just storing all of the water, it also has really important regulatory impacts on the climate of not just the local area, but at the entire planet Earth. So I'm going to talk a little bit about how that climate's changing and what type of effects it might have on the water. And another reason to study the Arctic is it's a rapidly changing landscape. It's a very sensitive environment, and it's very prone to small and subtle changes that might have potential snowballing effects. So it's a really neat area to do this type of research, especially if you want to study an area that's changing, to be able to determine how and how it might change in the future. So my research interests are centered around trying to understand how the water in these places interacts with other physical aspects of the environment beyond just within the cryosphere or the hydrology. We want to understand how water interacts with the ecology and vegetation and wildlife and people and communities. So we want to understand the physical interactions that are taking place now, how they've changed in the past, and then how they might change in the future if we continue to alter and warm this climate. So in essence, I just want to understand what's happening to the water in the Arctic, and that's sort of the focus of my research and a large portion of my research group's main research interests as well too. So just to start off with a little context, it's widely accepted and extremely well documented that drastic increases in air temperature are directly linked to man-made climate change, especially occurring in the last half a century or so. And just to provide a bit of a context here, this is a heat map of the circumpolar Arctic area there, with red being hotter than average air surface temperatures and blue being cooler areas. And we can see that much of the Arctic area is sort of this light to dark red color, meaning that it's warming at a alarming rate. And we not only see that this warming that we've observed everywhere across the globe is occurring in these areas, but it's actually occurring at a much faster rate than it is across the rest of the planet. And so just to give a little bit of a context, the Arctic region here is warming at over double the rate, with some areas 2 to 3 times the global rate in terms of air temperatures increasing. And of course, this warming is not uniform across the globe, especially in the Arctic. This figure here is difference from average long-term temperatures from 2018 to 2019, and we see that the Western North American Arctic is this red hotspot, meaning that it's warming at quite an alarming rate. And then if we look at this over long periods of time, we see that in general the Arctic is warming, but there are some areas that are cooling, at least on a year-to-year basis, which is part of the interannual variability in air surface temperatures there. But we know that things are warming, especially if we start to look at the last 2 decades, where there's been a divergence with air temperatures in the Arctic when compared to the global temperature averages. So one of the reasons why this is so concerning is if you follow the news or have paid attention at all to any climate research, you'll notice that we all talk about these Paris goals and IPCC, climate goals that we're all trying to achieve as a planet, and trying to limit global temperature rise to 1.5 degrees Celsius or so. And if we go beyond that, we'll pass a tipping point where there might be no point of return. But if you look at the data shown here, we in the Arctic, at least, we've already way surpassed this, and so we might be past the tipping point already in these Arctic regions, which has other important implications that I'll talk about later. So along with the warming climate, we're seeing changes to the cryosphere, so the ice and the sea ice and the glaciers. So we've all seen documentaries and heard the news where the Greenland ice sheet is melting and it's causing sea level rise. And one that gets a little less popularity is changes in the Arctic sea ice. And this is measured in a couple different ways, but on all the metrics that we measure and document sea ice in the north, we're seeing declines, especially compared to long-term averages. So the warming climate in the areas is leading to declines in the annual maximum extent of the sea ice measured in the summer. So this past September 2020 was the second lowest minimum sea ice recorded, and that's shown in this figure here with the median extent outlined in the yellow line there. But we're also seeing changes in the structure of the sea ice as well too. So not only are we having less ice, but we have less multi-year ice, which is important because it's often thicker and the ice is a little bit more dense, and it's more prone to resisting the summer melt and last a little longer. So in the wintertime, we're always seeing freeze back of the Arctic Ocean, but that first year ice is very thin and very prone to rapidly melting away. So having a decline in multi-year ice is a large concern as well too. And so with the oceans remaining free for larger portions of the year and temperatures rising, there's more moisture available in the atmosphere. And more moisture in the atmosphere means there's changing precipitation patterns. So some areas might be getting more snow, areas might be getting less snow, some get more rain, some get less rain. There's a lot of variability, and that's hard to measure because it changes so much naturally just year to year. And then if we also look in the north, we can't look at hydrology and precipitation in the north without talking about snow. This map here shows a composite of the snowfall for 2002 across all of North America. And you can see that most of North America, all of Canada, and most of the United States is covered with snow at some point in the winter. And that has a really large, it plays a large factor in controlling, regional and continental, even global energy balance and supply of fresh water. But these warming trends are sort of decreasing the duration of the snow on the landscape. And that's sort of a big concern, especially from a hydrological perspective, because a lot of us, especially in North America, rely on snow in one form or another for fresh drinking water. So changing precipitation regimes are very important to understand. And then in the Arctic, and this is sort of widespread across the Arctic, with this warming climate and changes in precipitation, we've seen what's been called a greening of the tundra. So there's an expansion northward of shrub species, as shown in this picture here. You see all these tall, scrubby-looking green shrubs. And those are tall shrubs for this environment. And when you're talking about environments that are above the tree line and relatively flat and low-lying vegetation, having an advancement of taller shrubs and potentially eventually trees in some areas, that's going to change the landscape through changes in the vegetation structure and the ecology. It affects wildlife migration patterns and makes some areas more habitable for others, which might push other species out. But from a hydrological perspective, the changing in vegetation controls a lot of the evapotranspiration, which is water lost through plants transpiring in the summer months. But it also has a really important effect on the winter snow accumulation and distribution across the landscape, because these tall shrubs in a relatively open landscape like this act like large snow fences and they trap snow, which has important implications that I'm going to touch on in a couple of slides here. So with all of these changes that we've observed, at a broad scale across the Arctic, we sort of need to ask, well, why are these changes important? What kind of impacts might they have? And for starters, the Arctic is a very sensitive environment. It's very sensitive to change, and it can easily become unstable with just a small change in temperature, precipitation, or even human influences. You can start to push the environment towards a new normal, which may take a very long time to reach. When we're talking about Arctic environments, there's a couple of key things that we need to keep in mind before we start talking about how these changes might affect it and what's the impacts on the hydrology. For starters, most of the Arctic is covered by snow or ice for about 8 to 9 months of the year. The further north you go, the longer that extends. Some places are covered for snow up to 10 months of the year. And the snow is very important in these environments for a couple main reasons. For one, it provides most of the fresh water for all of the lakes and the rivers and the fisheries and the humans that live in these environments, and all that fresh water eventually makes its way in one way or another to the ocean. So it's a huge source of water, fresh water, but it also has strong influences on the global radiation balance through changes in the albedo. Snow being a very, very bright and reflective surface acts sort of like a mirror and bounces back a lot of incoming radiation, which helps to effectively cool the planet. So the Arctic regions have been termed before a global icebox or a global refrigerator because they help regulate the temperatures at a global scale. Snow as a medium is also very important because it's a great insulator. If anybody who's ever done any winter camping or slept in an igloo or built a snow fort at the end of your driveway and you crawled inside and you get really hot, snow traps a lot of air in between the ice crystals, and it's a great insulator. And this is important because it keeps the grounds warmer than the air surface, which in the north can be quite cold. And it allows things like animals to build shelters. It protects vegetation, and it helps to protect the soils as well too. So in these areas in the north, across most of the Arctic and even most of the subarctic, the entire region is underlain with permafrost, which is permanently frozen ground. And this varies in depth depending on where you are and your altitude and your latitude. The further north you go, in a lot of times, the deeper it gets. But in the subarctic, where the permafrost is sporadic or discontinuous, it's kind of blotchy and in patches. Those areas are really prone to that permafrost thaws as the soils and the air temperature warm up, and the permafrost disappears, and it's most likely not going to come back. In the northern regions where I work, the permafrost extends hundreds of meters in depth. It's a remnant from the last glaciation period. But warming temperatures and changes to snow and the insulation effect of that can alter the upper portion of that permafrost, which we call the active layer, which thaws out every year. And so the warmer temperatures you have, the deeper the thaw depth you might get. And that has a lot of important factors for vegetation and how deep plants can root. But it also really affects the stability of the landscape, which I'll touch on in a moment here. Snow and the hydrology in the Arctic regions is also really important for local communities who rely on either the snow to travel and transportation, whether it's ice roads or skidoo trails or commuting back and forth. But something that a lot of people don't often think about is snow is one of the main sources of water for hydroelectricity projects. And so when all that snow melts out at the end of winter, that water that's available is going to be what's recharging the reservoirs. And so if you rely on powering a city with hydropower, you need to know how much water you have available to do that. And in some cases, especially in the north, if there's not enough water, you have to plan ahead maybe a year in advance and start ordering fossil fuels to power the generators that power the cities that you live in. So it's really important for that. Another reason why the Arctic and the changes are important there is because these frozen soils, the permafrost that I mentioned, they contain a large storage of greenhouse gases in the form of carbon. And if we release that through thawing continuously, and that makes its way to the atmosphere, that could have really large impacts on the global greenhouse effect and the global climate. And some studies have estimated that there's double the atmospheric volume of carbon frozen in permafrost. So if that were to be released somehow at a very rapid scale, we might be pushing the climate beyond a tipping point. And at that point, you can't, switch your fossil fuels to a cleaner source. There's little we can do at that point. So to understand the changes in the hydrology and the water systems in the north here, we need to better understand the interactions with water and all the other physical aspects of the environment. Now, unfortunately, Arctic regions are one of the most understudied regions on the planet, and this is due to many reasons, but one of them being sort of a complication relating to either technical or logistical limitations in working in remote northern areas. A lot of the north is very sparsely populated, and when it is populated, they're clustered very closely. So to have a representative sample of data collection points spanning the entire area is a very challenging thing to do. And of course, beyond just working in remote areas of the north, the harsh winter months and the lack of daylight through the winter also makes studying these environments really challenging, which is sort of the focus of a lot of my research is on winter hydrology and trying to fill in some of our knowledge gaps that we don't quite understand yet because there's been a lack of adequate research in the last few decades. So a lot of my research focuses on measuring snow, water, and ice in whatever forms, and I focus on the whole hydrology system, but these are sort of the main ones because they're so influential. And so how do we do that? Well, we sort of use a combination of direct observations and local knowledge to monitor changes to the landscape at a point scale or at several point scales or over time. And then we sort of couple that with what we call living laboratories and real world field sites where we actually collect data and do long-term studies. And we spend long periods of time in the field watching things as they change through a season or through a year. And so we take all this data that we've collected and we sort of try to simplify it a little bit and work it into a way where we can understand the processes and interactions that are happening in the real world, and then find a way to incorporate that into a computer model, which can then we use that to predict and forecast what might happen in the future. So one of the goals is to take observations that you see in the field, simplify them, and then turn that into a computer model where you can say, if we tweak the temperature, how is the snow going to respond? Or if we tweak the depth of the snow, how is the stream flow going to respond? So a lot of our work just goes towards understanding the systems as a whole so we can use that to drive knowledge forward. And so when we're trying to measure the whole hydrological system, and if you flash back to your high school sort of understanding of the water balance here, where we have precipitation starting the water cycle off here with rain and snow that falls in the landscape, and then when that melts or when it runs off into lakes and rivers, some of it gets stored in the groundwater, and eventually all that water runs out through the system, through our lakes and streams. Then we have some of that water which either evaporates or evapotranspires back to the atmosphere. And in the winter, we have something called sublimation, which is when the snow changes state from a solid directly to a gas. So this is sort of the whole picture of what we're trying to understand in these northern environments here. So like I mentioned before, a large portion of my research is centered around snow because in this environment and across much of the northern hemisphere, snow is one of the most, if not the most important driver of the hydrological cycle. So in the landscape that I work in, shown in this picture here, the snow in these environments accounts for upwards of 60% of the total precipitation that we get in a year. So over those 8 or 9 winter months, all that snow accumulates, and then 60% of that precipitation all disappears within a couple weeks. But what's really important is that snowmelt often accounts for upwards of 80% of the total stream flow that we might get through that system there. So understanding the snow is of the utmost importance. So what I do personally is I take these field observations of snow surveys and from weather station data as pictured here, and I couple that with sort of newer or larger scale research techniques. So I use a lot of remote sensing, we call it. So we use drones, planes, and satellites to try to get a larger scale picture and essentially map the snow cover in these northern areas. And from those maps, we can infer a lot of information about the hydrology, whether it's looking at water storage, either at a single point or across a whole basin. We can look at snowmelt patterns. We can look at differences in snow depth. But then we can take that data and couple it with other hydrological measurements such as stream flow and evaporation, and we can build a whole water balance for these research sites. And then doing that at a fine enough resolution, so if we do those types of studies every day for a full year, we can start to look at patterns that emerge, and we use that information to then try to drive models and simulations to see how the landscape's going to change. So in general, I'm going to just talk a little bit about some of the broader scale changes that we've observed at our long-term monitoring site here. And sort of this is driven by, well, what's happening to the water in these systems there. So we're very fortunate enough at Laurier to operate a long-term Arctic research station called Trail Valley Creek, which, as Don mentioned, I'm also the sort of site and logistics manager for that. But we've been collecting data here at this research station since 1990. It was an old Environment Canada research station, and Laurier took it over in 2014. And since then, we've been conducting continuing our long-term monitoring and broadening our research scope, you could say. So we have a lot of international collaborators and national university and government collaborators who work with us, all studying different aspects of the physical environment to hopefully come together and piece together a better understanding of how all aspects of this environment are changing. So having a long-term data record in remote northern regions such as this are actually quite unique, and it's hard to get this type of data outside of long-term communities in the north. So you usually have to go to the larger city centers to get this type of data. And as I had mentioned before, those are few and far between, especially in the north there. So we're very fortunate to have a long-term data record here. And this is just an aerial overview of our research station here. The orange little tents sort of in the middle of the photo are the research station where we have people staying long-term doing research. And then in the foreground here is just one of our weather monitoring stations. So we have a couple different towers that measure everything from temperature to snow depth to greenhouse gases. And then we also have a lot of other experiments that are on site that measure various other aspects of the physical environment. So when we look at some of our long-term climate data, and if we take our data that we have from our location and sort of broaden our scope and look at some of the other long-term data records from some of our nearby monitoring sites, so those that are in Inuvik and Tuktoyaktuk who have longer records, we've found a couple consistent trends. Some are unique to our area of study, and some are sort of uniform across a broader portion of the Arctic. But in general, the temperatures have drastically increased over the past few decades at our Trail Valley Research Station and at the local monitoring sites as well too. And as I showed on that first slide with that climate warming map, the annual air temperatures that we've observed are showing increases of upwards of 5 to 7 degrees Celsius since the late 60s. So that's a very large warming trend with almost a degree Celsius per decade, which again, if you relate that back to global climate temperature increases, we've already blown past our IPCC commitments in the north. Along with temperature changes and a general warming, there's also a large change in the frequency and extreme temperature events. So we used to have, in the earlier decades, in the earlier record, many days a year that had winter temperatures below -40 and almost no summer days where the temperature was above, say, 30 degrees Celsius. But in the past probably 3 decades or so, that's almost swapped entirely. So nowadays, the winters are quite warm and mild, well, relatively warm and mild, but we don't see too many days where the average air temperature is below -40. And then we see a lot of warm summer days that are occurring. And this has a couple of different implications. The background for this slide is actually a feature called a frost wedge polygon. And so all of these little ridges are formed when the ground essentially gets so cold that it cracks. And then it does this year after year, and water filters in and it builds a wedge. So a big ice wedge. And without having extreme cold winter temperatures anymore, the ground doesn't get as cold and it doesn't crack. So these frost wedge polygons are disappearing. And with having warmer summers and warmer winters, these are actually degrading. And so this picture here in the center, there's vegetation that's starting to reestablish and take this over. And this is important because it can really alter the drainage of the landscape. And so all of these channels that have now thawed out might make a new pond or might funnel water away from another lake, which that has downstream effects for, you know, lakes with fish and things like that. We've also seen a general trend in warming, but the trends that we've noticed, it's seasonal. So in the winter months, they tend to be warming the fastest, and the summer is still maintaining warm. It's still increasing in temperature, but on average, the winter is warming a little faster than the rest of the year, and that again, that has important implications for the landscape. And yeah, and then with a general warming in air temperatures, we've also observed general warming of soil temperatures, which affects the permafrost stability. And if you thaw out more and more of that active layer every year, you're changing the soil characteristics. You're allowing different nutrients to be accessible and different plants to establish, but you're also affecting the physical stability of it. And in the north, especially in Trail Valley where we work, a lot of the permafrost is ice rich. So it has a very large content of just frozen solid ice. And if that melts out, then the whole ground just sinks and subsides. And if you do that on a slope or over a large area, you can have lakes and ponds form, or you could have massive slope failures, which I'll show a picture of in an upcoming slide here. So beyond the climate, if we look at the changes to the snow and the snowpack, we've seen that the length of the snow-covered season is shortening, and it's shortening, by a relatively slow amount, by about 2 days per decade. So the winter season is decreasing by about 2 days per decade, and that doesn't sound like a lot, but to put it in context, when my supervisor started doing work in this area, they would go up and do their end of winter stuff, say at the end of May, and now, only 30 years later, we have to go up a whole month earlier to be able to make sure that none of that snow's melted before we get it. So it has some important implications, especially if you're looking at a landscape that is traditionally covered by snow and reliant on that snow cover to, keep the soils frozen and provide fresh water. We've also noticed that the amount of water stored as snow across the landscape is generally decreasing, but there's a lot of variability in this because the amount of snow varies so much year to year, and there's a lot of uncertainty with regards to how well we can accurately measure snow in these environments. But in general, we're seeing a slight decline in the actual amount of snow. And from a hydrological perspective, having less snow stored in the landscape means that there's less runoff come the springtime to recharge the lakes and the rivers. So that could be quite alarming, especially if you rely on fresh water. We've also noticed that, and this is sort of general across much of the Arctic, is the albedo of the snow is slightly decreasing. So what happens is soot and black carbon and dust from nearby roads or highways, or even from far distant communities, gets transported to these areas, and it's all contained within the snow when it falls as precipitation. And we also have algae that grows on snow, and this all affects the surface properties and allows the snow to absorb more energy. So because it's absorbing more energy, it can melt faster, but it also affects the global albedo. So we might not be reflecting as much incoming radiation from the sun back into space, which means that we're absorbing it and further warming the area. And so in the snow-covered season, so the winter months, which often last 8 to 9 months, as I mentioned, we know that the water is not stored evenly across the landscape. And this is just a good picture here that highlights that. So in much of the upland tundra areas, there's only 20-30 centimeters of snow, and it's very dense and very wind-packed. So it's very hard. Some of it you can even walk on. And then a lot of the snow is blown through winter blowing snow processes, and it's stored in these really large drifts. So on these hills here, you have these large deposits where the snow can be anywhere from 3 to 6 meters deep. So that's a big contrast in the amount of water stored at different locations on the landscape, which is also one of the reasons why measuring snow at a landscape scale is so complicated, because if you miss sampling everything representatively, you might miss a large portion of that stored water there. But when the snow melts and all that water is released, it doesn't get released evenly. It doesn't all melt exactly on the same day at the same rate. Some of it might last weeks, maybe even months later into the season. And so it affects the timing of the snow melt and affects how much water can flow off into the lakes and rivers. And so the distribution of this timing of snowmelt is very important. And unfortunately, it's quite complicated to measure without either being on site or using modeling methods. And unfortunately, with most snow scientists, we're either really good at measuring snow at a very point scale or at a very national scale. So we can look at satellite imagery and get a good ballpark for the amount of snow, say, across the whole North American continent. But looking at it at like a watershed scale or an area of interest scale is actually quite complicated. And so a lot of our work actually goes into trying to improve our measurements of the snow so that we can apply them to broader areas across the north there. So we've also done some studies on some of the lakes in the area, and we had a master's student who's just wrapping up now, who's been doing an analysis of long-term changes to the lakes between Inuvik and Tuktoyaktuk, which is a fairly large area, and in that area there's an estimated about 3,500 lakes or so. And then if you extend your scope a little further into the Mackenzie Delta, there's tens of thousands of lakes in that area. And a lot of these lakes are thermal karst. As the background here is a thermal karst lake, which basically results from the ground thawing and water pooling after the last glaciation. What's happening, though, to a lot of these lakes, because they're located on permafrost and the climate's warming, is a lot of them are decreasing, either in total number of lakes, so some are disappearing, and then a lot of them are actually declining in surface area. So if you warm the temperatures in the summer, you have more evaporation from the lakes, which means that the water levels go down, and if they go down far enough and you don't get any more precipitation to recharge it, those lakes could desiccate and dry up. But in general, we've found that there's been a few lakes that have disappeared, and a lot of them are actually disappearing because of catastrophic lake drainage events. So what's happening is these ponds that are contained, or these lakes that are contained, are all of a sudden going through a rapid transition where something happens and they just drain in a very rapid period of time. Sometimes it's days, sometimes it might be over a season, but that could be controlled by many factors. But one idea is that the changing permafrost that's at the outlet of those channels is thawing, and it results in a rapid outlet for all that water, and those lakes drain down. And so we've been monitoring these using air photos and satellite photos, and we've seen some changes across the landscape with regards to these lakes. And we've also seen some new lakes being formed, and these are often through merging processes. So you'll have a series of chained lakes, and then what'll happen is the one lake will drain, or maybe the connecting area between them will thaw, or some disturbance will happen, and they'll actually join together as one or several lakes, which makes monitoring any long-term changes a little bit more complex. But it's something that we're sort of diving into and looking to improve our understanding of going forward. And so this is just a snapshot of a lake that drained back in the early 2000s. So over the course of a few weeks, this lake had an event at the outlet of it, and it just drained rapidly. And then you see this scar left over where there's not enough water to refill the lake, with the following year's precipitation. And so vegetation takes over, and new vegetation is established on this lake. We also do a lot of work looking into the rivers and the stream discharge in these environments, and we've seen some pretty interesting trends, and some that we can't quite explain yet. But in studying these lakes and rivers, we found that there's an earlier spring stream flow, which results from an earlier and a warmer spring period. And we have earlier snowmelt dates. So of course we would see stream flow in the streams at an earlier point in the year. But what's interesting is there's a bit of variability in the the total peak of that stream flow. So if you imagine a graph of the hydrograph, so the water per time, it sort of spikes in the spring and then it flatlines. And what we're seeing is a shift in that spike towards a later point in the season, which is a little contradictory. But one hypothesis is that the changing snow cover resulting from changing shrubs affects the timing of the snowmelt in a way that those deeper snowpacks melt later in the summer. And so you don't get this flashy snowmelt response. It actually kind of draws out a little bit. So it's melting earlier, but it's sort of being drawn out for longer. And then we also see a lot more larger rainfall events in the later summer and in the early fall, which is sort of affecting the later end of the stream season as well too. But you have to keep in mind that in these environments, most of the stream flow is occurring in the month of May or early June from the snowmelt, and it could be upwards of 80% of the total stream discharge through that year. So you have these really large flood events and then almost nothing through the summer. And this was actually something we found interesting in 2021. It was a very low snow year, record low snow year, and it was a very dry summer. And a lot of the streams in the areas that we study actually had either fully dried up or the only water that existed was a result of beaver ponds, such as this photo here. And that's sort of, I wouldn't say it's abnormal for these environments. It's always dry in the summer, but the level to which it was, the rivers were all dried up was sort of abnormal. And if we have continued warming trends and a change in the snow cover, we might see more trends like this into the future, which is really concerning if you are involved in the ecology of the area, or if you're looking at local fisheries and stuff. Fish can't make habitats in streams that are all dried up. And another thing we've been getting into really recently is increased beaver activity in the tundra areas. So historically, beavers haven't been much of a nuisance really in the tundra. They sort of stayed either in the Mackenzie Delta or they were further south in the tree line. But in the last couple of decades, there's been a lot of beaver activity pushing further and further north. And we've seen that a lot in the systems that we study, especially this last year. There were more beaver dams than we'd ever counted in the 30 years that we've been there. And so having an increased beaver activity affects the local hydrology. So that's something that we're going to study going forward here. And then with regards to permafrost, I touched on this a little bit here, but we've observed increasing active layer thaw depths and warming soil temperatures, which sort of lead to these increasing thaw slumps and mass wasting events. So the photo here is a thaw slump on the edge of a lake, and these are becoming more and more common as that ice-rich soil that's underlaying the whole landscape begins to thaw and melt out. The ice melts. The area just becomes unstable and just sinks. And eventually it'll find a new equilibrium, but it's going to create quite the disturbance before the landscape ever gets to that scale. And so this is a really small thaw slump here, but there's been ones observed further south in the Northwest Territories that over just a summer's period have moved more material than a 150-kilometer gravel highway between Inuvik and Tuktoyaktuk. So all of that gravel and material is moving into the lakes and the rivers and affecting the landscape and changing the nutrients available downstream. So it has potential to impact the water quality, which is concerning. And then there's also large effects of permafrost thaw on northern infrastructure, whether it's roads that are built on permafrost that thaw and become wavy like a strip of bacon and need maintenance every year, or whether it's in the local communities where all the buildings are built on stilts, but the soil's warming so fast that those stilts are sagging and buildings are being condemned and at risk of collapsing. So changes to the permafrost resulting from a warming climate could be quite drastic and very expensive to northerners, which is definitely of interest to the communities in the area. And then, of course, not all the disturbances and changes that we monitor are a direct cause of climate. We also see a lot of changes in Arctic regions at a more localized scale, but we see them nonetheless with regards to human disturbances and infrastructure, whether this be through development of highways or resource exploitation. there's the big risk to change the landscape, at least at a local scale, which is changing the hydrology. So that's sort of an interest to us. And the picture here I have is a bridge along the Inuvik-Tuktoyaktuk Highway, and there's actually a stream channel buried under all this ice. And so this is a bridge icing that's formed in the winter. In the middle of the winter, when temperatures are minus 30 or so, and all this water from the ground has been pushed up and over the stream channel. And you can see it's almost touching the bottom of the bridge there. And there might be 2 or 3 meters of ice built up here. And so this is kind of concerning, especially from a human perspective, because if this icing gets any larger, you need to go out there with heavy machinery and break it up and disturb it. And that takes a lot of time and resources. If you have to do that every year, those costs adds up, but it's also altering the landscape. And these types of icings do happen naturally across some of the landscapes in some of the stream channels and at the outlets of lakes. But in creating something like a highway, which is a linear feature that bisects the landscape and all these stream channels, you're altering the landscape, which is altering the hydrology. And so that's something that we're sort of interested in studying to better understand maybe why these are happening, and if they're happening here, well, how do they happen naturally? And we know they happen naturally, but at least we have an example that we could study as to maybe why that is. And so, why are some of these changes, important? Why do they matter to us back here down south and to others? Well, the local changes that we find in the Arctic could have regional and sometimes even global impacts. And one way this happens is through positive feedback loops. And so this is sort of a classic conceptual diagram here, where we'll have a positive feedback loop driven by a warming climate, and it's called the shrub snow. We're happening it, we have a warming climate that sort of leads to an encroachment of shrubs in northern areas. And these shrubs trap snow in the winter months, and they act like a snow fence. They contain a lot of the snow that's blowing in the winter. They change the distribution of the snow. And so what happens is this snow, preferentially insulates the ground in certain areas. When it melts in the spring, it melts sporadically, and it results in permafrost thaw in certain areas. And this warming soil and the permafrost thaw that we observe and the warmer temperatures lead to increased soil moisture, which leads to increased nutrient availability, which kind of feeds back into furthering the increase of shrubs. And so the cycle kind of continues and continues. And what's sort of really concerning is that as the cycle is continuing, there is a potential risk for increased greenhouse gases to be emitted, which on an atmospheric scale could really affect the global atmospheric CO2 and methane compositions. So we want to understand how this feedback loop is working and what variables are related, and then how that might feed back into a warming climate. And then each one of these different variables, has its own sort of set of feedback loops. So from my perspective, my research interests are on the snow cover and the hydrology. And so if you're increasing the shrubs and you have deeper snow depth, how does that change the stream flow? How does it change the albedo and the snow melt timing? And then a really important one is how does it affect lake ice thickness? And as you have more snow, you have thinner ice. And if you have a really thick snowpack, you'll have a really thin ice, which is very important if you're traveling across the land, but it also controls the fisheries in those lakes. And then those changing snowmelt patterns also really affect the stream flow hydrology, which sort of brings it back to my focuses. And so I just wanted to sort of wrap this up with a really short quote from the 2020 Arctic Report Card. And if you've never checked that out before, and I encourage you to give it a brief read. There's really awesome visuals and simplified content in there. And along with that, you should also check out the IPCC reports and the Canada's Changing Climate documents that are published. Those are very informative and really grasp the overall science and the interactions well too. But this quote sort of sums it up very well. The sustained transformation to a warmer, less frozen, and biologically changed Arctic remains clear. And then I would add to that, all of these impacts have regional and global climate, or all these have impacts on the regional and global climate through increased greenhouse gas emissions from thawing permafrost, changes to local and regional energy balances, and changes to freshwater runoff to streams, lakes, and oceans. And so trying to understand the complex reactions between all of these systems, both at scale and in the north, but how they feed back to climate that we might get in the south down here or across the globe, is sort of the driving force for our research. And with that, I just wanted to say thank you and kuyanomi, and happy to have hear any questions. And if you have a question that we don't get to answer, feel free to reach out anytime, either on Twitter or just send me an email. Thank you.
Thanks so much, Brandon. That was so informative, and I learned a lot. My name is Maria Patrico, and I'm the manager of branches at the Milton Public Library. And we're now happy to begin the facilitated question answer. This time there are no questions as of yet, but if anyone would like to pop something into the little box here that says say something nice, or into the ask a question. I have a question, and it's kind of about often in the news we're hearing these, like, we have 6 years to reverse some changes or to slow things down. Kind of how accurate is that information, and is there anything we can really do at this time, or have we kind of gone to this is just going to keep happening?
Yeah, that's a really complex question. I mean, I'm not exactly an expert in the long-term modeling of the climate, but I trust the data and the information that the scientists who are experts in that have presented. As long as you're interpreting that data in a sort of non-biased, non-alarmist way, I think that's the key. And I think what happens is a lot of the times climate science gets misinterpreted through news and media, and it gets sensationalized a little bit. So yes, it is, it has, the environment, the climate has changed drastically. There will be a point where we're past a tipping point where it's expected that things are going to continue to spiral beyond control, whether we do anything or not. But I think we have to err on the side of, well, we should at least try to do whatever we can, right? And minimize the impact where we can. And there comes a point, and we might have already passed it, who knows, where it's too late, and we'll see a further warming climate for the next 100 years, right? But I think we're now at the point where we need to start understanding, okay, well, if we stopped everything now, what's the impact going to be, versus if we do nothing for 20 more years and stop. There's going to be changes, that's about guaranteed, but the severity of those changes is what we need to think about. And I think we need to sort of use caution going forward to be able to reduce those impacts in the future.
Thanks.
Yeah.
I know it's complicated.
Yeah, I mean,
to get the ball rolling.
It's a great question, and I think it spurs a good conversation as long as it's not sensationalized too much. And I think everybody should, sort of follow a bit of a worst case scenario, mentality, just in case, right? Like what's the negative to trying to save the climate, versus who's benefiting from it. So
yeah. So a couple questions. Marcia's asking, have you had the opportunity to work with NASA drones that survey snow depth or their data?
That's a good question. I've worked a little bit with NASA ongoing projects, and we have projects with our own Canadian Space Agency where we're doing airborne snow mapping stuff. Not much with drones. a lot of the NASA-based drone stuff that I'm aware of is coming out of, you know, they're focusing on the United States, and they have their main key mountain ranges where they do repeat surveying. So we do the same type of stuff, and there's a bit of collaboration here and there, but I haven't actually directly worked with them. It sounds super interesting. I'd love to be able to do the kind of work that we do at a drone scale that they get to work at, but unfortunately, no.
And Michael's asking, what effect is Arctic warming having on migration patterns? Yeah,
that's a really good one. There's been a lot of wildlife in general impacts of a changing climate in the north here. One of the examples of changing migration patterns that I just showed a couple slides ago is having beavers move into our area of the woods, or the tundra, I should say. In the past, and if you talk to many of the locals, there's not much of a history of beavers in the tundra. There's not much for them to build dams with because it's all tiny little shrub vegetation. But in the past few decades, there's been a big surge in beavers in our areas. You know, from my perspective, they changed the landscape and the hydrology quite a bit. But from wildlife perspective, they have the potential to impact the fisheries, which changes the migration and mating for fish. I know I've heard stories of a lot of increased sightings in fish like salmon moving further north as the waters are getting a little warmer. And I believe I saw a study that saw a bunch of sharks moving into Arctic waters as of late. But I'm not exactly too familiar with those patterns. I would say that there's a potential for a lot of impact on wildlife, like bird migration, especially if birds are traveling over long distances for their migration routes and the seasons are changing. I would imagine that that's affecting their migration routes, especially if you have a warmer, earlier spring snowmelt period when most of the birds fly back north. But that's a great question, Michael, and I hope I answered it well. If not, I could probably refer you to a couple of wildlife ecologists who are more of an expert on that.
That's great. Thanks so much. So that was our questions. So I'd like to say on behalf of Wilfrid Laurier University and the Milton Public Library, thank you, Brendan, for sharing your knowledge and expertise with us this evening. Thank you also to all of the attendees for joining us. And a copy of tonight's lecture will be shared on the Milton Public Library website and on YouTube as well in the next few days. And if you haven't already, please be sure to register for the next lecture on November 10th. Thank you, everyone, and have a wonderful night. Bye. Thanks again.
Thanks, everyone.
Good night.